Hello everyone. Now today we are going to learn about Gauss divergence theorem. Let's look at the statement. If a bar is a continuous differentiable vector function in the region capital E bounded by the closed surfaces, then integral over s of dot and ds equal to double integral over v del dot f dv. Now del dot f nothing but div f, okay, into dv. Now surface integral of dot and ds equal to volume integral nothing but triple integral that into div f into dv. Now this is a relation between surface to volume integral. Here we need to have the bounded region by closed surfaces. Okay, by closing the surfaces we have the bounded region, right? Now bounded region, over that we need to integrate it. Okay. Now look at the problem. Verify Gauss divergence theorem for the functions. Function f bar equal to x square minus yzi plus y square minus zxa plus z square minus xyk taken over the rectangular parallelepiped. 0 less than or equal to x less than or equal to a, 0 less than or equal to y less than or equal to b, z less than 0 less than or equal to z less than or equal to c. It means that the x we have from starting 0 to a, now y we have starting from 0 to b, z we have starting with 0 to c. Now that's why we have rectangular parallelepiped. It's like cuboid. Now x varies with 0 to a, y 0 to b, z 0 to c. Now we need to verify Gauss divergence theorem for this over the rectangular parallelepiped. All are closed surfaces making a region, right? The inner part of the box, that is a closed region, make a use of these surfaces. Now total surface integral of this rectangular parallelepiped, which is same as the volume integral of div f into dv. Okay, this we are going to prove it, verify it. We need to find for LHS and RHS. First look at the RHS, next we need to find for the LHS part. Okay, you may first find for LHS, next find for RHS, your wish, but I validated first RHS, next LHS. Now first RHS. For finding the RHS, first find for a div f. Now RHS div f equal to del dot f. Now del dot f. Now I dot I is 1, dou by dou x of x square minus y square plus dou by dou y square minus zx plus dou by dou z of z square minus xy. Now with respect to x, derivative is 2x. With respect to y, derivative is 2y. With respect to z, now is 2 of x plus y plus z. Now the RHS part, integral over v div f into dv equal to, in this volume, that x varies from 0 to a, y varies from 0 to b, z varies from 0 to c. That limits are applied, 0 to c, 0 to b, 0 to a. Now integrate div f, div is 2 of x plus y plus z into dx dy dz. First I integrate with respect to x. You may integrate with respect to y or z, all are constant inside. Now two constant outside. Integrate with respect to x is x square by 2. Here we have, what is a constant term, and that into x 0 to a dy dx. Now apply the limits a square by 2 plus y plus z into a. Lower limit is 0, no need to write it. Lower dy dz. Now this you have to integrate next with respect to y. A square by 2 is a constant, that integration is y plus here a into y integration y square by 2 plus az into az integration with respect to y is y. Now limits of 0 to b dz. Now apply the limit here b a square by 2 plus here b square a by 2 plus a b z into dz. Now this you have to integrate with respect to z. Now here z we have z here z integration z square by 2 0 to c. Apply the limit, then here a square b c, right? Now this is c by 2 plus ab square by 2 into c plus here ab c square by 2. Okay. Now lower limit is 0. LCM 2, then 2 cancel, then common ABC in each term. Here we remaining A, remaining B, remaining C. Then RHS we have integral over V div of dv equal to ABC into A plus B plus C. Okay. Now let's go for LHS. Now following the LHS, now this total region is divided into the 6 surfaces. Let for the surface here S1, S2, S3, S4, S5, S6. Over that we need to integrate it one by one. Okay. Now we'll consider for LHS part integral over S f dot and ds equal to integral over S1 f dot and ds plus integral over S2 f dot and ds, integral over S3 f dot and ds plus integral over S4 f dot and ds plus integral over S5 f dot and ds plus integral over S6 f dot and ds. Okay. Now we need to integrate it one by one surfaces. Now along S1. S1 I considered O, A, B, C. Okay. Bottom of the box. Okay. Now that is lie on xy plane. In xy plane z value 0. Okay. For this surface, now n is nothing, unit outward normal. Unit outward normal is minus k. Okay, now xyz perpendicular line is z. For this positive z we have inside normal, right? We need to get for n is a outside normal. Now outside normal is opposite direction of positive z, nothing but negative z. Now negative z unit normal vector is minus k. Now n is minus k. Now in this plane, now x varies from 0 to a, y varies from 0 to b. Okay. Now these changes applied. Integral over S1 f dot and ds equal to x equals 0 to a, x equals 0 to b. Now f dot minus k into dx dy. Now this minus I will write it here. Now dot product k dot k is 1. Now remaining is 0. Now it's z square minus x by dx dy. Z value 0. Okay. Now remaining x y square by 2. Now this minus become plus x y square by 2 0 to x y integration y square by 2 0 to b. Now apply the limit b square by 2, lower limit is 0, remaining we have x. Now apply the integration with respect to x square by 2 0 to a. Now apply the limits a square by 2. Okay. Now multiplied with b square by 2, then total a square into b square by 4. Now is over a S1. Similarly over a S2 I consider OCDF is lie on YZ plane. Now where x equal to 0. Then a unit outward normal is minus I, right? Opposite direction of x is a inward normal, outward normal. Now y varying from 0 to b. Now z varies from 0 to c. Now apply the limits and do the dot product of dot n into d by dz. Now we are minus I into I, because minus here, I dot I is 1, remaining is 0. Now x square minus yz d by dz. Now z is x is 0 here, x applied 0, minus yz we have, minus into minus plus. Now z integration z square by 2, now limit 0 to c into dy. Now c square by 2 is a constant, lower limit is 0. Now c square by 2 write it outside. Now integral 0 to b by dy. Now y integration with respect to y is y square by 2. Now limits have 0 to b. Now is b square c square by 4. Now along S3 consider OAGF. Now S3 is lie on xz plane. Now where y value 0. Now unit outward normal is minus z. Okay, minus z, x equals 0 to a, z equals 0 to c. Now apply the limits. Integral over S3 of dot and ds equal to x equals 0 to a and z equals 0 to c. F dot n is minus j into dx dz. Now multiply it here, minus x equals 0 to a, z equals 0 to c, y square minus zx dx dy. Y equals 0, this term 0, minus into minus plus. Now z integration z square by 2, limit 0 to c. Apply c square by 2, lower limit is 0. Now integrate with respect to x integration x square by 2. Now apply the limits, a square by 2, now lower limit is 0. Now totally a square, c square by 4. Now next along S4 I considered F, D, E, G. I show it here. F, D, E, G. Okay, top. Now what this is a surface parallel to the xy plane where z is a constant. What is z is? Z is c value. Over the surface z value is c. Now z value considered c. Now unit outward normal. Now unit outward normal is positive k, not negative, is the opposite direction, right? Now is inward. Outward is plus k. Plus k. X varies from 0 to a, y varies from 0 to b. Apply it here, z square dot product with k remaining 0, z square minus xy dx dy. Now first integrate with respect to x and y. Now x next y. Now first before that, what is the z value in that plane? C. Now apply that, c square minus xy dx dy. Now first integrate with respect to y. Now c square is a constant, that integration is y minus x into y integration y square by 2. Apply the limit, c square b minus xb square by 2. xb square by 2, lower limit is 0. Now this you have to integrate with respect to x. C square b is a constant, that integration is x minus b square by 2 is a constant, x integration x square by 2. Now apply the limit, a b c square minus a square b square by 4. Now along sy is a b e g is a parallel to the yz plane, therefore x equal to a. Now here a unit outward normal is n equal to y varies from 0 to b and z varies from 0 to c. Now better to look at in a figure, we can easy to understand it. Okay. Now we said that draw the figure and denote the ABC, vertices, and look at the surfaces. You can easy to understand. Now I've got n. Now here I is a outward normal. Now multiply that product here, x square minus yz dy dz. Now y varies from 0 to b, z varies from 0 to c. Apply it. Then integrate with respect to y and z. You can get a square bc minus b square c square by 4. Okay. Now similarness we can have along S6 also, BEGD is a parallel to xz plane where y equal to b value. Now unit outward normal is n equal to j. X varies from 0 to a and z varies from 0 to c. Now that you have to apply on this integration. Now here with the dot product with the j, only this term we have, remaining 0, z square minus zx. Now this you have to integrate it with respect to x and z. Now you can have the solution b square ca minus c square a square by 4. Okay. Now integral over c of dot and ds equal to, now sum it all. Now some of the terms are cancelled here. A square b square by 4, b square c square by 4, a square by c a square c square by 4. Now these terms here we have, then with the negative they are cancelled. Remaining abc square a square bc plus b square ca. In three terms you can common abc, then we have a plus b plus c. LHS we have abc into a plus b plus c. RHS also we have abc into a plus b plus c. Okay, LHS equal to RHS. We verified Gauss divergence theorem. The next class I am going to discuss some other problem on Gauss divergence theorem. Thank you.